So now we are moving into section 5.4, where the all-important fundamental theorem of calculus finally rears its head. We have enough information where we essentially can tie in what derivatives and antiderivatives and integrals mean to us. This is called the fundamental theorem of calculus. So before we get to that, we're going to talk about the mean value theorem for definite integrals. So the mean value theorem essentially says take the average value of a function, then there has to be some value of c on that interval a to b such that that's the value of the function at that point. Well, that makes sense. If that's the average value of the function over the interval, then it's got to be one of these guys. And this is all that's saying, right? So in other words, the average value of the function on that interval has to occur for some value that's of c here that's between x equals a and x equals b. Okay, that's the mean value theorem for integrals. Notice that I then can say, well, what does that mean? What it's saying is if I take this b minus a and multiply it on both sides, so I have now f of c times b minus a, well, what is f of c times b minus a? It's the area of this rectangle. It ends up being that if I know the average value of the function over that interval, if I take that as the height of my rectangle, the entire length of the interval, which is b minus a, as the width, then the area of that rectangle is exactly equal to the area that's under the curve over that interval from a to b. And that's what this notation is saying to us, right? The area of this rectangle, which is f of c times height times width b minus a, is equal to the area under the curve from a to b of f of x dx. And so now we're to the fundamental theorem of calculus. Fundamental theorem of calculus has two parts. You can think of this first part as saying if I take the derivative of an integral, it gets me back to the function inside, right? So if I take the derivative of this definite integral from a to x, so a is any constant, x is x, of the function f of t dt. So t is just like a dummy variable here, right? You don't worry about it. All we worry about when I take the integral here is that this says dt is the same as this t here. So integrating with respect to t. The derivative of the integral is f of x. In other words, if I were to evaluate this and then plug in b, this would be some function of x. So taking the derivative of an integral is saying it's taking the derivative of an antiderivative, which gets me back to the function. So that's interesting because that then makes sense to us why we have this fundamental theorem of calculus part 2, which is the way we evaluate integrals. The way we evaluate integrals, definite integrals, is we look at this integral and we say, what's an antiderivative of this little f of x? That's capital F of x. So find an antiderivative. Don't worry about the plus c because they would cancel out when I evaluate it at the upper limit minus evaluate at the lower limit. So we find an antiderivative of f of x, forgetting about plus c. We don't need that. We don't need all antiderivatives, just one. So pretend like the plus capital C is a 0. Then plug in the upper limit minus plug in the lower limit, and that's actually the value of this definite integral. And then that makes sense to you then why, if you go back up to those other formulas that we had, let me go back up here real quick, these formulas here. If I take the antiderivative of x without worrying about plus c, that's x squared over 2. So x squared over 2 evaluated at b would be b squared over 2 minus x squared over 2 evaluated at a would be a squared over 2. So that's actually where these formulas came from. Same with these guys. Just kind of take a look at those and those will make sense to you. So here's some types of problems that you're going to use. So in example 85 here, we want to use the fundamental theorem of calculus, part 1, to find dy dx. So this is y. This is actually a function of x. Remember, this t is just a dummy variable, right? Because you're gonna find an antiderivative of this, and then plug in x, and then plug in 1, and then take the derivative of it, because this would end up being a function of x when you're all done. If I take the derivative of this, well, it's saying you don't have to go all the way through actually evaluating this, because I'm asking for the derivative of an antiderivative, which gets me back to the function. So all I have to do is plug in x everywhere I say a t in the integrand. The integrand is t cubed plus 1, so plug in x, I get x cubed plus 1. That's all the fundamental theorem of calculus part 1 tells us to do. If I want the derivative of a definite integral, what's going from some constant a to x, then I just plug in x. That's it. Now we want to use the fundamental theorem of calculus part 2 to do the same thing, but first to use the fundamental theorem of calculus part 2 to evaluate the integral, so you can push the I believe button for me and see that this works. So now I have y equals this guy, so I'm going to break this up into two integrals. So the integral of t cubed would be t fourth over 4. Integral of 1 would be t, right? These are antiderivatives for these guys. Evaluated from 1 to x, this is notation, what we usually write when we do an indefinite integral. This square bracket means evaluated from 1 to x, a to b. So first of all, I plug in the b value here, so I get x to the fourth over 4 plus x, minus, plug in the a value, I get 1/4 plus 1. So I get x to the fourth over 4 plus x minus 5/4. Then if I take the derivative of that, because that's what I was asked to find, I get 4x cubed over 4 is x cubed plus 1, x cubed plus 1, and there, lo and behold, it works whether I actually evaluate the integral or I use the fundamental theorem of calculus part 1. So this is using the fundamental theorem of calculus part 2 to evaluate the integral. This then is showing how it's, when I take the derivative, it gives me the same answer as if I had just used the fundamental theorem of calculus part 1.